Okay, so let's do some more work with PDAs. And we're going to start with some problems from the book. And this first problem asks us to find a PDA for all strings over A, B with the same number of A's and B's. Now, we've already found a context-free grammar for this. Now we're going to find a PDA for it.
Process in this, okay? And so what I'm going to think about is I have to have the same number of A's and B's, but at any given time, I might have the same number, in which case I could accept, or I might have more A's, or I might have more B's, right? So what I'm going to do is I'm going to use the stack to keep track of whatever I have more of, okay? And so what I'm going to do is the following. Let's start, and let's say for starters, remember if we see an X at the top of the stack, because of the way I've set this up, an X at the top of the stack means whatever we've processed, whether it's 0 letters or 50 letters, that we've seen the same number of A's and B's. So if I see an X, I'm going to have, at the top of the stack, I'm going to have a special free jump. At any time, if I want to, and I see an X at the top of the stack, I can jump to my magical accept state. And this is important because, of course, the empty string should be accepted, right? So if I get to state 1 and I don't have any letters to process, and so I take free jump with an X at the top of my stack, magic, I accept. Okay. And now let's talk about the other cases. There's a couple of possibilities, right? Let's suppose that everything is even, okay? And if everything is even, right, so we have the same number of A's and B's so far. Maybe I'll write kind of a list, right? One option is we have same number of A's and B's have been processed so far, right? If that happens to be the case, then we're going to have an X at the top of our stack, okay? And if that's the case and we see an A, well, we know now we have more A's than B's, so we're going to start stuffing A's onto our stack to keep track of them. On the other hand, if we have an X at the top of our stack and we see a B next, then we'll say, okay, well, now we're going to use the stack to hold B's until we see some A's to get rid of them, okay? So when we start out, of course, we have the same number of A's and B's processed so far. So let's suppose, and of course when we start out there's an X at the top of the stack. So let's suppose when we start out we see an A and there's an X at the top of the stack. Then what I'm going to do is I'm going to push something that tells me, ooh, I have one more A than I do B's. So why don't we push, and I'm going to push a capital A. I could push whatever I wanted, but I'm going to push a capital A. Mostly because that's just easier for me to remember. So let me see if I can squidge this guy a little bit more so it's out of the way. All right, so what I'm going to do is, and if I see more A's after that, let's push more A's on the stack. So if I see a little A and there's a big A already at the top of the stack, I'll push another A. All right. So as long as I keep seeing A's and I have more A's than B's, I'm just going to pile up those A's. So, you know, maybe my stack has an X and then it'll have a bunch of A's on it, each one representing an extra A. At some point a B is going to come along, we hope, if we're going to accept this. And whenever I see a B, if there's an A at the top of the stack, I want to get rid of that A, right? So I'm just going to change color so it's a little bit more clear because I'm running out of space here a little bit. But so if I happen to see a B and there's an A at the top of the stack, I'm going to do a pop. I'm going to kind of process my B and at the same time get rid of one of those A's. And I'm going to keep doing that as long as there's an A at the top of the stack. So far what we've got in these three rules is if there's nothing on the stack, right, there's just the X, and you see an A, push an A. If there's already an A on the stack, that means I have more A's than B's. You see another one, push it. If there's already an A on the stack and I see a B, oh, hooray, finally we're equalizing a little bit, I will pop it. So that's kind of the first half. But that doesn't take into account any situations where we have more B's than A's at a given time in our string, right? So we need to essentially do the corresponding rules for the other side. So if it's even, so the number of A's and B's I've seen so far, I've processed so far is even, so there's an X at the top of my stack. If I see a B and there's an X at the top of my stack, let's push a capital B instead. So now we're using the stack to hold the extra B's, as it were, right? Or to hold a record of how many extra B's there are. And I'm going to just change color to make it so they don't blend in so much, the rules with each other. Again, if I see a B and there's already a B on the stack, then I push another B, so I always keep track of how many. But if there's a B at the top of my stack, I'm just using another color to make it clear so that these things don't run into each other. If there's a B at my top of my stack, but I see an A, well, hooray, I'm starting to even stuff out. So what I'm going to do is I'm going to do a pop just to get that off. So what I encourage you to do is copy out possibly a little bit more neatly. It's probably easier for you to write this neatly on paper than it is for me to write it here on my iPad. But copy out this PDA. Of course, you want to write start there, right? Copy out this PDA and test a couple of strings on it, and make sure that when you test it, you can accept those strings that are that have the same number of A's. So you could try like the string AABB, same number of A's and B's, or ABBA, right? All of these should work, or AAABABBB. Does that work? And then try some that don't have the same number of A's and B's, right? Add, you know, an A onto the front of all these, or a B onto the front of all these. But I want you to just try this out and see how it's processed, because again, a lot of this is just kind of learning some of the tricks and understanding and really feeling in your gut, okay, I see how these things are processed, right? Okay, so let's get rid of all this mess. And let's take a look at this. And oh yeah, now we're trying to find palindromes of odd length over AB. All right. So this is where a PDA really comes into its own. And this is where we really do have to use that kind of magical approach to drawing these things. There is just no way that we can do this problem deterministically. So let me tell you what I'm going to do, and then I'll draw it, and then I want you to check it. Okay? So what I'm going to do is the following. For any given palindrome that's an odd length, right? If you think about it for a minute, there's a bunch of letters. Then there's some letter I don't really care about, right? That could be an A or a B. And then I start repeating the letters backwards, right? So what I'm going to do is I'm going to have a couple of states. I'm going to have one state where all I'm doing is pushing the new letters as I see them, if they're the letters on the first half of the palindrome, onto the stack. Then when I get to the middle letter, how do I know when I get to the middle letter? Well, this is the non-determinism. It's kind of magic. I'll take a magic jump, and I don't really care if it's an A or B. And then I'll start matching, and I'll say, there's my A, cross it off with that A, pop it off the stack. There's my B, pop this one off the stack. There's my A, pop this one off the stack. There's my B, pop this one off the stack, and so on. Okay? So that's what I'm going to do. I'm going to magically know where the first half of my string ends, and where there's that middle letter, and then where the second half ends. And again, this is, I mean, I don't expect you to be able to do this without seeing it at least once, right? That's why I'm going over it. But once I go over it, I want you to kind of understand it. And this is where the importance of really understanding those kind of magic jumps in NFA, or in NFAs, or you just try every possibility and see if any of them work. If you prefer that approach in NFAs, you really need to understand how that works with regular languages, because I'm not going to spend a lot of time on it here. We spent a lot of time with regular languages with these context-free languages, I'm just going to assume you understand that stuff. Okay, so let me actually show you what that PDA looks like. So let's get rid of this. So what I'm going to do is I'm going to have my start state. And I'm going to start by whatever I see for the first half of my palindrome, I'm going to push on the stack. So if I see an A and there's an X on the top of my stack, then I'm going to push. Now, I could push an A. It would make the most sense to push an A. I'm actually going to push, let's do a smiley face, just to emphasize to you that we can put whatever the heck we want on the stack. It's got to be a symbol. It can't be X because that's a special symbol. But beyond that, we can put whatever the heck we want on the stack. So whenever I see an A, I'm going to push a smiley face. And that's if there's an X on the top of the stack. And of course, we need a second one because once I've started, when I, whatever it is, if I see an X or I see a smiley face, or in fact, if there's B's on there, I need to also push an A. So for the first half, I'm just going to push an A whenever I see pretty much anything, right? So I could also say, if there's an A and there's already a smiley face at the top of the stack, I'm also going to push a smiley face, right? And similarly, I'll do that for B. So if I see a B and there's an X at the top of the stack, well, I can't do smiley face. I need to come up with something else that represents a B. Maybe I'll just use a capital B because I'm getting lazy. And if I see a little B and there's a big B at the top of the stack, oops, I will push a B. These should all say push, right? Push a smiley. I was so excited about the smiley, I forgot to write push. And we'll push that B. Maybe I can shrink this just ever so slightly. Okay. Now, of course, I might not see just A's or just B's, right? This isn't the same as the other problem. So, if I see an A and there's already a B on the stack, I also want to push a smiley, right? To say, oh, look, I found another A. So maybe I'll use another color here just so you can see it all in there. Oh, actually, let's fix this arrow. That's my start arrow, and I never labeled it. So if I see an A and there's a B at the top of the stack, I also just want to push another smiley face to indicate, boy, I saw another A. It's a smiley face. I know you can't tell. And similarly, down here, if I see a B and there's already an A on the stack, I'm going to push a B. Now, this is getting really, really messy, and computer scientists, we all love our shortcuts, so I'm going to show you a shortcut notation for PDAs that make our lives much easier. What I'm going to do is I'm going to take this whole thing and shove it up in the corner, and let me just start from scratch again. Okay, so here's my start, state 1, and what I'm going to do is I'm going to write the following. If I see an A, no matter what's on the stack, and that's supposed to look like a question mark, I am going to push that smiley face. And if I see a B, no matter what's on the stack, I'm going to push the letter B. So my stack, if my string started out as A, B, B, and then maybe my little middle letter is A, and then I have B, B, A, then I would end up with pushing for these first three. I would push a smiley face, oops, there's an X at the bottom, smiley face, and then a B, and then a B. Okay. Then when I see that middle letter, I'm going to transition to state 2. And for that middle letter, I'm just going to change colors again to make it a little bit easier to see. If I see an A, I don't really care what's on the stack. I'm going to do a no-op. And also, if I see a B, I don't really care what's on the stack. I'm going to do a no-op, right? And then when I get to state 2, so now I'll process that A, I'm going to start doing the matching. So I will see this B, and I'm only going to pop it if I see another B. I see the B, I'll pop it if it's a B. See an A, only pop it if there's a smiley face. And if I'm left with an X, then I know I've got my odd palindrome, right? Okay, so at this point, if I'm at state 2, if I see an A, and there is a smiley face at the top of the stack, then I will pop because they match. And if I see a B, and there is a B at the top of the stack, then I will pop because they match. And finally, if I get to the end, right, so it's a free jump, so I can take it at any time, but if I see an X at the top of the stack, I'm going to do a no-op and go to state 3, right? And so again, what I want you to do is to take a look. Let me just cross this off because that was our kind of example, and I don't want you to get confused with our example here, but I don't think I can split it to shrink it. All right, and let me just get this guy way out of the way. So what I want you to do again is to just take this picture that we've drawn here, right, this PDA, and I want you to try a bunch of palindromes and make sure you can walk through them and you can see, oh, here's a palindrome of odd length, I see that this works. Here's another palindrome of odd length, I see it works. Here's a string that is maybe a palindrome of even length, it doesn't work. Or here's a string that's not a palindrome of any sort, it doesn't work. I don't end up, and remember, we only accept if you end up at an accept state and you've processed all the letters in your string. That's the key. So I really want you to try and see if you can try out this. Just test this PDA on some examples and see if it works. Or rather, convince yourself that it works. Okay, so let me just clean up the screen a little bit. And let's do one more problem. And this problem says, find a deterministic PDA that accepts by final state, right? So this is in the book, it says, find a deterministic PDA that accepts by final state. Well, all of our PDAs accept by final state. That's how we're doing it. There are other ways, obviously, to represent PDAs, but for this class, we're just doing one that accepts if you get to the final state and you've processed your string. For this language, a to the n, b to the 2n. Now, the tricky part here, you could do a to the n, b to the 2n, I hope. Well, maybe not at this point, but once you've seen it, it shouldn't be too bad. So what I'm going to do is I'm going to do it two ways. First, I'm going to do a PDA, which would be kind of my gut reaction to how to make a PDA for this, the easiest way to make a PDA. And then we're going to talk about why the PDA that I made is not deterministic, and then we'll have to figure out a better way. A to the n, b to the 2n, such that n is greater than or equal to 0, right? So the logic that I would use, the way I would think about this, if I were doing this, and I weren't worrying about deterministic, non-deterministic, is I would say, okay, well, every time, I need to keep track of how many A's I have, so I'm probably going to push A's on the stack. And I need to, for every A I push, I'm going to have to pop off a B, right? And so there's actually two ways I can do that. I could either kind of have a hack where whenever I see an A, I push two A's on, and then when I see a B, I just take them off one at a time. Or I can say, okay, for every time I push an A on, when I get to the B part, I'm going to have to pop two B's off for every A that I see. I'm going to do it the first way. So every time I see an A, I'm going to push two A's on my stack. Now, of course, we don't have a way to push two things on your stack in one step, but you can always do it in two steps. So what I'm going to do is the following. So just take a look. I'm going to say, here's my start, right? And I'm going to say, if you see an A and there's an X on the stack, I'm going to push an A, but instead, and I'll push a capital A. Instead of a smiley face or whatever, I could push a lowercase a. I've decided I'm going to push a capital A and go to state 2. So I'm not staying in state 1 right now. And what I'm going to do is state 2 is going to be my state, and I'm going to only go to state 2 if I've just seen an A, if I've just processed an A. And so what I'm going to do is the only thing I'm going to do in state 2 is I'm going to say, no matter what's up next, free jump, the only thing you can do is a free jump, and in fact, no matter what's on the stack, push another A, right? And so now every time I see one A in my string, I'm going to push one, and then I'm going to push another. I'm going to push one, and then I'm going to push another. And in fact, you know what? I need another rule that takes me from 1 to 2 that says, if I see, here, let me do it in blue. If I see an A and there's already an A on the stack, push an A, right? And you know what, actually, if I get to state 2, I know there has to be an A on the stack, so I could do that. And the truth is that I could combine the two rules that transition from state 1 to state 2 with just a question mark here, right? But the basic idea is, if I see an A, if I'm in state 1 and I see an A, go to state 2 and push an A, right? No matter what's on the stack. And once I'm in state 2, the only way you can get out of state 2 is to go back to state 1 and push an A. So I'm going to keep doing this, pushing 2 A's at a time whenever I see 1 A, until I've got all my A's pressed. And then I'm going to have a transition to my deal with the B's scenario. And I could probably stick around at state 1, but I don't have enough space, so I'm going to go to state 3. So if I see a B, there darn well better be an A on the top of the stack, and I will pop. And that's going to be true as I hang out at state 3. If I see a B, there better be an A at the top of the stack, and I'll pop. So even though I have twice as many B's, I've pushed extra A's on to compensate for that. Right? And then when I am completely done and I'm ready to accept, I am going to transition to an accept state, and lambda, if I see X, I will do a no op. Okay? And this looks pretty good. It doesn't right now look non-deterministic to me. Right now it looks like a deterministic PDA, except we forgot something. We forgot a step, which is right now our PDA doesn't accept the empty string. It doesn't accept lambda. And in order to make it accept the empty string, the most obvious thing to do is to add a transition here that says, if you see lambda and there's an X at the top of the stack, do a no op. But as soon as I do that, I make my PDA non-deterministic, because there's two rules, this one and this one, that could both happen if I'm at state 1 and I see the letter A, right? I can choose between them. I have a non-deterministic PDA. So we need to think of another way to cope with this situation where I want to be able to accept the empty string, right? So step 1, before I keep going, before I go on with this, I want you to just copy out this PDA that I've drawn, right, and process a few strings through it. So yeah, it's non-deterministic. We didn't answer the problem that we were asked, but at least it is in fact a PDA that works. Maybe we'll try and do one. So let me just show you. I'm going to have to shrink this a little bit so I have some space to work. Let's see if this works. All right, so there's my PDA. And let's suppose that we see, the string let's do two. Let's do one that works and one that doesn't. We see A, 1, 2, 3, 4 B's, right? We're going to start with our stack with an X at the bottom. And it would be legal for me to follow this, but then I'd get straight to state 4 and I'd still have things to process, so I wouldn't accept. So it wouldn't be in the language. So let's take the other option, which is I see an A, and there's an X on the stack, this guy, so I'm going to push an A. So I process that, I push an A. Now I'm at state 2, and I have to take this free jump, which says no matter what, if you see an A at the top of the stack, just push another A. So I do that, and I don't consume any more letters. I process the second A here because I'm back at state 1, and I use this transition. I have an A. I see A on the stack, so I push an A. And then again, I'm at state 2 at this point, and the only way to get anywhere is to go back to state 1 and push another A, right? At this point, I see a B, and the only thing I can do to get out of 1 on a B is to take this transition, which says if I have a B and I see an A at the top of the stack, pop. So I will process that and pop. I'm now at state 3, and I don't see an X, so the only thing I can do is take this BA pop. So I process my B, I see the A at the top of the stack, I pop it. I'm going to do that again from state 3, and again from state 3. And now, finally, I'm in a situation where there's an X at the top of the stack, so I can take this guy. And in fact, that's the only legitimate move I can take out of state 3 now. So I end up in state 4, which is an accept state, and I have processed everything in my string. In contrast, if I had, let's say, the string A, B, 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 right? More B's than I should, right? Then what'll happen is I will be starting my stack with an X, but I will process this A, putting an A is the transition from state 1 to state 2, another A is the transition from 2 to back to 1. Then I'll process the B and go to state 3, popping this. I'll process the B, go to state 3 again, popping this. And then I'm in a situation where I'm at state 3, I see a B, but there's an X at the top of my stack, so I'm stuck because there's nowhere I can go from state 3 if I see a B and an X at the top of my stack, right? I mean, I could take this jump if I want, right? I guess that's that's what I have to do is I end up at state 4, but now there's nothing I can do and I can't process that B, so it does fail. Okay, so this was all well and good, but again, remember that these two yellow states that I've circled, right, or transitions, make it a non-deterministic PDA, and this problem asked us for a deterministic PDA. So we need to have some way that we accept the empty string and yet still can deal with the fact that we need a deterministic PDA. And it turns out it's not going to be too hard. So let me just clean this up, and let's try and do it again deterministically now. So the thing that hung us up before was that lambda transition from the beginning where we saw an X, because we also need to deal with if we see an A and an X. So what I'm going to do is just another kind of a hack. I'm going to say if you get to state 1 is now going to be an accept state. So I will accept the empty string just by virtue of arriving at state 1. And now what I'm going to do is I'm going to leave state 1 pretty much immediately, right? If I don't have the empty string, then what I'm going to do is, obviously if I don't have the empty string, the only way I can accept is if I see an A and an X, and I will push an A, right? And that'll take me, I guess, to state 2. And remember we had this push 2 A's in a row. Well, we can do that right now just by saying, you know what? The only way I'm going to let you out of state 2 is I'm going to say there's only going to be one transition out of state 2, and it's going to be free jump if there's an A on the top of the stack, push an A, right? and that'll take us to state 3. And now what we'll do is so basically instead of looping back to state 1 when we saw our A's, so processing pushing A, we're going to do that between states 2 and 3. Okay, so what I'm going to do, I'm just going to change color so it's easier to read, is at this point, if I see another A I need to process and there's an A on the stack, there can't be an X because I've already processed 1, then I will push an A, and that'll send me to state 2, where the only way out of state 2 is if I see that lambda. Now, if I'm at state 3, sorry, not if I see that lambda, of course, is there's only one transition out of state 2, and it's just an automatic, you know, as long as there's an A on the top of the stack, you can push an A. So at some point, I'm going to see the letter B, and so I'm going to make another rule again. I'm going to change colors just so you can keep track of what's going on. That takes me to state 4 that says if I see a B and there's an A on the stack then what I will do is I will pop that A, and I'll do another loop here to keep up that process. If there's a B and I see an A, I will pop that A. Oops, I'll just say pop. Sorry, we just say pop. Not pop A, we just pop what's on the top of the stack. We just happen to know it's an A. And then finally, if we've processed everything again, I'm just changing color to make it easier to follow my picture here and see what I'm writing. We'll have an except state here that says if I see an X at the top of the stack at any time, I can take this free jump and do a no-op to state 5. But notice now, yeah, I have a couple of lambda transitions in here, but in any given state, there's no way I have a choice, right? So this lambda transition here, this lambda transition here from 2 to 3 is the only transition from 2 to 3. So if I want to keep progressing, I need to take that one. And out of state 4, there are 2 options to get out of state 4. One option I can only take if there's an A at the top of the stack. The other option, which is my lambda option, I can only take if there's an X at the top of the stack. So if you look at this whole PDA that I've just drawn, it's a deterministic PDA. There's no magic, no nothing. No matter what you do, at any given time, you only have one potential choice. And of course, if there's too few A's and I end up seeing an X too early and I take this jump, I'll still have letters left in my string, so I won't be able to accept. I'll be in an accept state, but there'll still be letters in my string, so the string is not in my language. Okay, 2 more examples, and then quite a few more slides, but they'll be much quicker. Okay. So what we're going to do here is it says construct a PDA that accepts the same language as this grammar, and again construct a PDA that accepts the same language as this grammar. So let's just look at this for a minute. This grammar looks to me like the language A to the N, D, B to the N, such that N is an element of N, right? So you should look and confirm that you believe that. So what about this language? This one's a little weirder. If we look at it, of course lambda's in the language, but we can also have A's that match B's, right? Or pairs of A's at the beginning. So I think what we're going to have for this language is, let's see, it's going to be A to the N, B to the N, right? But you can also have as many A's, well, pairs of A's, I guess, to the M. And let me just move this over a little bit. There you go. Such that N and M
are natural numbers. There's your squiggly.
Okay. So a to the n, d, b to the n. All right. So what we need is a bunch of a's and then the same number of b's. And so I hope your intuition is telling you that what you need to do is keep track of how many a's you have. And how would you keep track of how many a's you have? By pushing something on the stack every time you see an a. And then we'll see a D. That's actually, we may be able to do this deterministically because we have to see the D before we start popping the B's, right? So I'm going to do something like this. I'm going to start, and every time I see an A, and I'm going to use a question mark here, no matter what's on the stack, it could be an X, or it could be whatever I'm about to decide to push. I'm going to push, and let's push, just for fun, let's push a Q. So you understand, you can have anything that you want to use on the stack, except for X, right? X is the only symbol that we know means our kind of stack is almost empty symbol, so we don't want to use an X. But, all right, so as many A's as I see, no matter what's on the stack, I'm going to push a Q. At some point, hopefully if I want to accept my string, I'm going to see the letter D. And when I see the letter D, there might be an X on the stack or there might be an A on the stack. But either way, I'm going to do nothing. I'm just going to keep moving. Because it's really when I see the B's that I want to pop. And if I'm at state 2, if I see a B, and I match that up with a Q that I pushed on the stack to keep track of my A's, then I will pop. And hopefully if I have the same number of A's and B's, I'll end up with an X, right? If I do have the same number of A's and B's, I'll end up with an X on the stack. And so then I can move with a lambda X no op to state 3 where I accept. So let's just do a quick look and see, is this a deterministic PDA or a non-deterministic PDA? If I'm at state 1, I can only take one choice, right? If I see an A, I have to take this choice. If I see a D, I have to take this choice. If I'm at state 2, again, only one choice, because if there's a Q on the stack at the top of the stack, I take this loop. If there's an X at the top of the stack, I take that one. So it looks like this is actually a deterministic PDA for this language. Again, now's a good time. Pause the video, copy this picture out, try and do it. Make sure that if you try some strings, right, so here are some strings that this PDA should accept. It should accept A, D, BB, and it should accept D, right? And 1, 2, 3, 4, and a D. 1, 2, 3, 4. Oops, that's an A, right? Not a D. On the other hand, it should not accept, I'll do them in red, A, D, B, B, and it should not accept A, B, B, right? These are no-goes, right? Because those strings are not of this form. Okay? So, test that. Try it. Make sure you understand that. Let me clean this up and we'll try the other one. Okay, so let's take a look at this second problem. Let's look at this grammar for a minute and see what kind of strings we can get from it. So obviously the string lambda is in there, right? So if I say, in my language, we've got lambda. We also have, it looks like we can have pairs of A's at the front or A's at the front, but the A's at the front have to match the number of B's. So we can get strings, like we could build up strings. Let me show you a couple of I could say something like S goes to AS, B goes to A,
AAA SB goes to 1, 2, 3 lambda B, right? Which is just AAAB. So that's in my language, right? I could have just some pairs of S, so I could have like 1, 2, 3, 4 in my language, or I could have AABB or AABB, right? But the things I cannot have in my language are, here, we'll do them in blue. Let's see, I can't have an A by itself. I can't have a B by itself. I can't have any B's before A's. If I have more A's than B's, the number more has to be an even number, right? So if I have like 1, 2, 3, 4 A's, then what can I not have? If I do 1B, 2B, 3 B's, that won't work. So those are the kinds of things that are not in the language. So let's talk about, let me see if I can now get rid of these bits. Oh, pretty good. Okay, so let's start with the easy stuff. I'll make a, start state. And what I want to do, the first thing I'm going to do is just deal with this lambda by itself, right? If I just see a lambda, the first thing, then I want to accept that. So maybe we'll make state 2 our accept state. And I will have an arrow here that says if I see a lambda and there is an X on the stack, then I will do a no op and go to my accept state. Now, what I'm thinking about doing in the back of my head right now, I'll tell you a little bit before I do it, is I'm thinking that all of the A's come before all the B's, right? So we have to process the A's. And at any given time when I see an A, I don't know whether it's an A that matches a B if I just see an arbitrary string, or if it's an A that sort of matches an A. So I'm going to have to use some non-determinism in here. And what I'm going to do is I'll have sort of two paths to follow. And how do I know which path to pick? Well, either it's magic and I just know it, or I try every possible path and see if there's a successful path to a final state. But I'm going to imagine that if I just kind of draw my stack over here for a minute, whenever I see one of these A's that's going to match a B, I am just going to, let's see, my stack starts with the next, and then I'm going to put an A on my stack. So if I end up with 3 A's on my stack, that means I expect to see 3 B's later. But whenever I encounter one of these A's that matches up, I'm not actually going to put anything on my stack. And that's kind of what I'm thinking in my head. Let me show you how I'm going to do that. So if I expect that I'm going to be processing something like this, then really I just have to see the A, put an A on my stack, and come back for more A's. I guess state 1 for me right now is sort of the state where I'm processing the A part. So I'm going to say, all right, if I see an A, and I don't really care what's on the stack, right? Whether there's, if I'm trying to process this kind of stuff, I see an A or an X, it doesn't really matter. So what I see, I still want to put another A on top. So what I'm going to say is if I see an A and there's anything on the stack, I'm marking that as question mark. I am assuming that you've seen that notation. I'm making these slides a little bit after I made most of the others. So the question mark notation just means it's sort of a wild card. It matches anything on the stack. So if I see an A and there is anything on the stack, then I am going to push a capital A. On the other hand, if I am trying to process these guys, then I really just want to make sure I see 2 A's before I come back to my state 1. So what I'm going to do is I'll have a state 3 here, and I'll say, well, if I see an A, and again, I don't really care what's on the stack, I'm going to do a no op to get out to state 3, and then let's see if I can draw this back. Sorry, it's sort of limited room with a giant stylus. And then I'm going to have another A question mark no op here. And what that's going to do for me is is that if I see pairs of A's, I won't do anything. I won't add anything to my stack. I won't take anything off my stack. I'll just kind of keep going around. And so eventually I'm going to have processed all the A's, right? And then I need to process any B's that there are. And if there's no B's, if I just went round this and didn't push anything on the stack, then I can take this lambda jump down if I just had pairs of A's. But if I did push at least one A, then I need to go somewhere else to deal with it. So let's make a state 4 over here. And I think just so that you can see what I'm doing, I am going to use a red pen for this transition because it's just too messy in here now. So to get to state 4, I'm going to go to state 4 if there is, if I see a B and there's an A on the stack, and then I'm going to pop that A off the stack. And then if I see any more B's and there are still A's on the stack, I'm going to do the same thing. So I'll loop in here and I'll see if there's a B and there's an A on the stack, then I will pop that. But eventually, I'm going to get to the point, hopefully, if it's in my language, where I run out of all the B's. I've popped all of the A's off of the stack, and so now I'm left with an X again. And so now I can do, if I see a lambda and there's an X on the stack, do a no-op and go to my accept state. Heads up, we are going to be skipping some of the material in the textbook that talks about PDAs. We're going to skip the section on equivalent forms of acceptance. What you actually just need to know is that you can describe a PDA in a bunch of different ways, and that's equivalent to the model that we're using. So you could talk about a PDA that doesn't have any accept states, but that accepts if the stack is empty, right? And the other thing you need to know is the set of languages that are context-free is exactly the same set of languages accepted by PDAs. So just like when we were talking about DFAs and NFAs and regular languages, they were all kind of equivalent. PDAs, languages that can be accepted by a PDA, same set as the languages that are context-free. And we're not going to do it, but you won't be shocked to hear there are algorithms that'll turn a PDA into a context-free grammar and algorithms that'll turn a CFG, a context-free grammar, into a PDA, just like we did turning the regular expressions into NFAs and NFAs into regular expressions.